We are on page 241, module 7, describing chemical reactions. Different types of reactions. And maybe one of the best ways to get into doing all this is to go ahead and draw some basic reaction forms on the board for us so we can start considering the different types of reactions we're going to be looking at. For example, if I were to, and you know my paradigm here, each one of these letters just represents a different element. It could be okay. So element A, 2 of element B, and 1 of element C produces A plus 2B plus C. That's one type of reaction we're going to talk about in a few minutes. So a compound, a molecule that's made up of 3 different elements with 1 of the first, 2 of the second, and 1 of the third, produces 3 individual elements. Another type, using that same the same makeup, would be if I reversed it and said A plus 2B plus C, what do you suppose that's going to produce? Let's go ahead and say that it produces A, B sub 2, C. And then there's another type of reaction where we have something plus oxygen that produces and the various productions from there. These are the 3 different kinds of reactions we're going to be talking about at the beginning of module 7 here. The first one, do you see from this equation that we have something, we have a molecule, and what are we basically doing to the molecule? If you remember, we actually finished the last year, the last module, with some discussion on this. So if you have notes, good notes, you can just look back at what we covered just before we went on break. I have a molecule, and hopefully now, even if you don't, maybe it'd be easier now where we are in chemistry if I use sodium and carbon and other real elements. But just element A, 2 of element B, and element C produces the constituent elements that make it up. Remember I said in chemistry, when we take something, we break it apart into its elemental forms. This is known as a decomposition reaction. Unlike biology, maybe you'll remember this, I said, unlike biology, where decomposition tends to be ooey, gooey, and slimy, okay? In chemistry, decomposition just means I take a whole and I break it up into its elemental parts for decomposition. Now, if this is to decompose something, what does this look like? Well, I'm taking the elemental forms and I'm combining them together to make a new molecule, a composite whole. This type of reaction is known as a formation reaction. We're going to go into each one of these in more detail. This is just kind of like the broad overview, okay? So a decomposition reaction, a formation reaction, and then we have this final one, which we're going to actually have a couple different variations that we're going to consider. We have something that reacts with oxygen to produce various forms of product. Okay? Multiple different kinds. And so for this class for chemistry, I want you to realize that this kind of reaction is known as a combustion reaction. Not every combustion reaction is identified by fire being present. When we think of combustion, we generally think of something catching on fire. If I say the textbook spontaneously combusted, or maybe more appropriately, your homework spontaneously combusted, right? Why don't you have it? It spontaneously combusted. You're expecting me to understand that what you mean is, I don't know, I was just sitting there doing it, it was like all done. It was perfect, and then caught on fire and disappeared, right? That's like just a little bit more complicated than the dog ate it, but I mean, that's kind of what we're expecting, right? We think of combustion, we think of a fire burning it up. Well, in chemistry, that's one of the forms of combustion. We're going to see that also, technically speaking, a metal rusting is a form of combustion, because in chemistry, combustion means something is reacting with oxygen. Something is reacting with oxygen. Now that fits in a standard model in your mind of something burning up, because in order for something to burn, you need a fuel, you need heat, and you need oxygen. That's why you need oxygen, because it's a form of combustion. The heat, the flame, the light, those are all forms of energy that are part of that overall combustion reaction. So those are the things we're going to be looking at right now. And part of what I'm doing right now is trying to gauge how we should handle this module. I'm not going to be here next week. I have doctoral seminars next week, and so I'll be in classes. Here's the sympathy for me, okay? Monday through Saturday from 8 a.m. till 10 p.m. every day. Papers, projects, and presentations due every day. Okay, so I get to play student next week all day long, rather than just between 3:30 in the afternoon until 7 a.m. the next morning. I get to be student all week long. So this is where I get to be in your role and have a cohort of 10 other students where we get together and get to turn in papers and present projects. And actually what I'm doing is I'm redesigning the chemistry course for doing it in a slightly different way. So we'll see if that comes about next year. Part of what I'm doing. Okay. Let's go ahead then, kind of follow along the text. On page 242, you've got the definition of a decomposition reaction. Let's go ahead and I'll erase these other forms. We'll get back to them. The definition of a decomposition reaction is a reaction that changes a compound into its constituent elements. It's going to take whatever the molecule it is, and it's going to break it down. Break it down into its individual elemental forms. So looking over at example 7.1 on page 243, it says, write the chemical equation that describes the decomposition of ethanol. Well, ethanol, C2H6O. If I'm going to break it down into its constituent elemental forms, what elements do I have to take into consideration? I'm going to be breaking down into some form of, from left to right, carbon. Okay, C stands for carbon. So it's going to include carbon and hydrogen. And lastly, oxygen. Right. Now, breaking down into its elemental form. Those are the three different elements. Are these written in their appropriate elemental form? Okay. How am I going to find naturally occurring carbon? Is it okay? Yeah. I can find carbon as just one individual carbon atom. Okay. But what about hydrogen and oxygen? Do I find them in their elemental form as a single oxygen and a single hydrogen? Right, homonuclear diatomic. So I'm going to find those in the form of H2 and O2. Hopefully everybody remembers that, right? My homonuclear diatomics, that's the column 7 elements, nitrogen, oxygen, and hydrogen. So other than hydrogen, it forms the 7. Nitrogen, oxygen, and then column 7, plus hydrogen. So every one of those are going to be, in their elemental form, are going to be in a molecule, a homonuclear diatomic molecule. So if I break down C2H6O, my forms are going to need to be carbon, just C, H2, and O2. So guess what I have to do next? Ask yourself the question, is that reaction balanced? No. Let's look at the left and right, the reactants and the products. We're looking at carbon, hydrogen, and oxygen. Right? Cho. When I break down this, I start with my reactants, the right side are my products. Go through and do an element count. How many carbons do you see in the original, on the reactant side?
Yeah.
2 carbons, 6 hydrogens, and 1 oxygen. On the product side, how many carbons? 1, hydrogens, 2, and oxygens, 2. Okay. Next, what am I going to ask myself? Where am I lacking? Where am I lacking? And let's go ahead and try to fix it. Now, one of the things that makes it easy is if you look to the right-hand side, everything is in its elemental form, right? That used to be one of the things we thought of before when we were balancing an equation. Look at the products and find what is, or rather, look at the reactants and products and hold off till the end on whatever's in the elemental form. Now that everything's in the elemental form, it probably should go pretty quickly, pretty easily. Well, over on the reactants, right, let's look to the reactant side. Since all the elemental forms are in the product, let's go ahead and deal with the non-elemental form, which is in the reactant side, the reaction side. And the only one that's lacking is oxygen, right? So how would I fix that? I could go ahead and put a 2 in front of it. If I do that, no, I have to put a 2 as a coefficient, because remember, I cannot touch the subscripts. I can only attack the coefficients. Okay. My 2 carbons become 4 carbons. My 6 hydrogens become 12 hydrogens, and my 1 oxygen becomes 2 oxygens. Now, I'm balanced in the oxygens. I'm lacking in carbons and hydrogens, but it's all on the product side, which means I can go over to the elemental forms and just knock them out. So carbons, I have 4, I need 4, and I get that by making that 4. And hydrogens, I have 12, excuse me, I have 2, I need 12, and I do that by putting 6 in front and making that 12. I'm jumping ahead. If you look at the example in the book, the way they did it, it takes a lot longer to solve, because what they did was, rather than working from the method that I used, looking where I'm lacking, and then going to the non-elemental issues first, it solves a lot quicker. What they do, you can see that they start by leaving it its original form and putting 2 carbons, then going through and making 3 sets of 2 hydrogens, but then they're left with the dilemma that 1, 2, and 3, and then they only need 1/2 of an oxygen. Remember we talked about that as a shortcut we could use before? We could take half of it, but then we'd have to multiply everything by 2 because we can't leave a fractional coefficient. Let me go through and actually do it the way the book did it then. This would be the way I would do it, the way I've taught you to do it. It's much quicker. Let me go back to their process, just to walk you through it, to see that it's another legitimate way of doing it. Okay? And as long as you take legitimate steps, each step along the way, you'll end up at the same destination. Just a little different course to get there. Okay? So we have 2 carbons, 6 hydrogens, and 1 oxygen to start with. And we have 1, 2, and 2 in our balanced equation. What they do is they start on the elemental forms and say, wait a minute, I have 2. The technique they use is always look to what they need in the product side first, or excuse me, yeah, the product side first. So they have 2 carbons to start with. They get 2 carbons by just adding the 2. Now you see that the carbons are balanced. Let's look to the hydrogens. They have 6 to start with. They have 2, so they need 3 sets of 2, which makes it 6. Now the issue is I have 1 oxygen and I need 1 on the product side. How do I do that? How do I take a set of 2 and only get 1 of them? I only take half of it, right? Theoretically. This oxygen molecule has 2 atoms of oxygen. I only need 1 atom of oxygen. I get that by putting a 1/2 coefficient in front. Okay? That'll give me 1. But I cannot leave a fractional coefficient in the balanced equation. So to get rid of that coefficient of 1/2, I need to multiply the entire thing by 2. So the implied 1 becomes 2, the 2 becomes 4, the 3 becomes 6, and the 1/2 becomes 1. And we're back to what we ended up with the last time. 2 different ways to get to the same ending. Right? Any questions on those 2 different ways in balancing the equation? I mean, this was what we finished with at the end of Module 6. So there's a refresher after the Christmas break on how to balance as well. There being none. They take 3 pages, 4 pages to go through that. Okay. So again, if you remember it from the end of Module 6, it's straightforward, no duh, let's move on. If you don't remember how to do it, you have 4 pages to review to get to this point. But we should be able to do that. Now look at the next example they use. Write the balanced equation for the decomposition of HiH3F. Let's go ahead and do that along with the book as well. That's silicon H3. All right, if I'm told I have a decomposition reaction, what that means is, and for our purposes, a decomposition reaction is a reaction that takes a whole and breaks it up into something else. So it could be, let's say we had a 3-element molecule. It could break it up into a single element and a double element molecule. That's technically a decomposition reaction. We took a whole and broke it up into smaller pieces. For the purposes in our course, what we're going to do is say a decomposition reaction is when we take a molecule and we break it all the way down into all of its elemental forms. And remember how elements were discovered in the first place. They took compounds, they broke them down, and when they couldn't break them down anymore, from Dalton's laws, remember he said the element is the smallest indivisible unit of matter? Okay. And we know technically, yeah, we can break down the atom, but for the purposes of our course, we're going to say that an element, you can't break an element down into anything smaller and still have a fundamental building block of matter. And so for a decomposition reaction, we're going to take these 3 elements that form this one molecule and break it down all the way to its elemental forms. So the elements I need to deal with are silicon, hydrogen, and fluorine. Ask myself the next question. I've broken down the elements just by looking at the symbols. I've broken down the elements. Is this their elemental form? And the answer will be yes, except for homonuclear diatomics. So I look at this for all of my homonuclear diatomics. Do I see any? 2 of them, right. And they are?
Hydrogen and fluorine.
Hydrogen and fluorine are both homonuclear diatomics. Correct. Silicon is not, but now we have the elemental forms. Is it balanced? No, because I can look right away and see 3 hydrogens, 2 hydrogens. This isn't going to work. So we need to go through a balancing now. Silicon, hydrogen, and fluorine. Reactants, products, you form the matrix and do the count. On the reactant side, silicon, I have 1, hydrogen 3, fluorine 1. On the product side, silicon 1, hydrogen 2, fluorine 2. Walk me through balancing. Where are we going to go?
Put a 2 in front of that on the reactant side.
Put a 2 here in order to what? What are you trying to accomplish?
Balance out that fluorine.
Balance fluorine. Okay, we're going to try to balance fluorine by adding a 2 over here. That's going to now change this to a 2, and hydrogen here is to a 6, and fluorine here is to a 2. Is that correct? Did I do it right? Okay.
Next.
Next, it just all falls into place, right? I mean, now it's all elemental forms that need to be bumped up. So you're saying, Greg?
Silicon on the product side.
Okay, so we need to increase from 1 to 2. We do that by a 2 coefficient. That gives us 2. And then hydrogen, we need 6. We've got blocks of 2. We need 3 blocks of 2. And 2, 3, 1. And now we have a balanced equation. If I break down 2 molecules, it's going to form these combinations of of those constituent elements in their elemental forms. Is that the process they used in the book? No, it's not. They did the fractional coefficient method. So maybe that's good. I believe this is easier. But the fractional coefficient, if you've learned something from remember the exam you finished with? The fractional coefficient method can be quicker. So if you're short on time, it's quicker, but it also is more prone to error. You're more likely to mess up the math, multiplying fractions, than you are by doing it this way. But sometimes you get into a jam and you go, you know what, I wish I could just put a half in front of it. Okay, I can, but I have to resolve that later. I have to get rid of that fractional coefficient in the process. What they did, if you notice, is, let me back it up and use their method, just as an alternate way of solving it. So we start with the counts of 1, 3, 1, 1, 2, 2. Notice that they go and apply a 3/2 coefficient to the H2. Why do they do that? They started with hydrogen. They did 3/2. Okay, so 3/2. What's that going to give me? 3/2 of H2. I've got 1.5 H2 molecules, which is going to give me 3 hydrogens. Right? So my 2 becomes a 3. 1.5 sets of 2. One set would be 2, plus a half of a set is another 1, gives me 3. So this balances the hydrogens. And then they go to balance the fluorine. I have 1, so I need 1. I have 2, but I only need 1. I need half as many as I have. To get 1, I have 1/2. 1/2 of a fluorine molecule. See? Now they balance, but they've got fractional coefficients. I need to get rid of the fractional coefficients. How do I get rid of the fractional coefficients? I'm going to look and see note that they have a common denominator of 2. In order to get rid of a denominator, you multiply the numerator by the denominator, right? Here, in this case, to get rid of the halves, I'm going to multiply everything by 2. What that's going to do is this implied 1 becomes a 2. This implied 1 becomes a 2. This coefficient is now 3/2 times 2. 3/2 times 2, the 2 cancels the 2 and leaves me with a 3. And this is 1/2 times 2, which hopefully you see is just 1. And that's the final form. So we get to the same answer 2 different ways. One of them, the primary way that I taught in class, the second way is using the fractional coefficient and then multiplying to eliminate the fractional coefficient. Let's go ahead and do the on your own. 7.1 is on page 247. I'll write it on the board. You're going to decompose nitrogen trichloride. So you shouldn't need to wait for me to give you the chemical formula, right? Nitrogen trifluoride. Don't worry about the geometry, I just did it up there for fun. Here's what kind of a molecule? The geometry. It's got an unbonded pair on the top. That's better. I wrote it wrong, didn't I? It's not 105, it's 107, correct. So it's a pyramidal. It's the tripod, remember? It's the camera sitting on top of the tripod. So that's its molecular, its Vesper geometry. Okay? But NF3, decompose it. Decompose it. Nitrogen trichloride.
He wants to balance it.
The whole thing. Decompose it means break it up and then balance it. Oh, it's trichloride, but it doesn't make a difference. Works out the same. Remember, because they're all column 7s, it's technically trichloride. But since they're both column 7s, the geometry is the same. Everywhere you have F, just change it with Cl. The same thing. Works the same. Because both fluorine and chlorine are homonuclear diatomics, right? So we're going to decompose this into nitrogen and chlorine. I ask myself the question. What question do I ask myself?
Is it balanced? Is it balanced?
Well, I'm going to ask myself, is it balanced? Before I can even say, is it balanced, I need to find out, are my products in their elemental form? Shortcut way of thinking, are any of them homonuclear diatomics? If yes, make sure I show them as being homonuclear diatomic. Is nitrogen a homonuclear diatomic? It is. Is chlorine?
Yes.
It is. Okay, now ask the question, is it balanced? Good. Are there homonuclear diatomics? Yes. Indicate that. Second, is it balanced? No. 1 nitrogen, 2 nitrogen. 3 chlorine, 2 chlorine. It's not balanced, so now we need to balance it. Okay. We'll do it both ways. Let's go ahead and do it with the way I've been teaching it, and then we'll do the fractional way. So let's go ahead and start from here. What are we going to do first?
Go to one of the, and over, or at the reactant cell, whatever.
Put it to
Before that one, I did.
in front of the reactant, in front of the, okay. So we're going to put a 2 here.
I did that for you. You're gonna take
Between the chlorine, yeah, okay, so it's not NO, it's NCl. That's why I was kind of like, okay. But that's going to change my reactant side. I now have 2 nitrogens and 6 chlorines. So what are we going to do next, Tyler?
And then you put a curve or CL on that. Looks like an old wall here, that's why.
Mm-hmm. However, you should have known that that would have not had the same geometry, because an oxygen is a column 6 element. This would have to be a column 7 element. Oh! Anyway, okay. Let's go ahead, back it up, and somebody walk us through it using fractionals. So nitrogen 1, chlorine 3, nitrogen 2, chlorine 2. So rather than seeing what you need more of, what do you need less of? That's the question you ask yourself to use fractionals. What do I need less of? I need less of nitrogen, okay? I need less nitrogen. So how do I get, I need less nitrogen. I have 2, I only need 1. So to get 1, I need 1/2 a set of 2, and that gives me 1. And then I need less of chlorine, right? I have 3, but I only need 2. So I need 2/3, right? Because I have 2/3 of a set of 3, it's going to give me 2. Right? But now we have the fun, because now we have to get rid of a 3 and a 6 in the denominator. Or excuse me, a 3 and a 2. I gave it away, right? I don't know where this is going to go. We're doing this together, okay? But do you see that it's now balanced?
Yeah.
I have 2/3. I've messed up the nitrogen, haven't I? I've messed up the nitrogen by putting 2/3 in front of the nitrogen. I've balanced the chlorine, but now I've messed up the nitrogen. Tell you what, I'm going to back out of this one now because it's so much easier to do it the other way. But it is. Do you want to stick with it? I'm willing to stick with it. I can do the math. Can you? Here we go. Come on. Okay. So you've got 2/3 of a nitrogen. Now what are we going to do? I have 2/3 of a nitrogen, but what I have over here is 1 nitrogen. So how do we get 2/3 of a 1? I get 2/3 of a 1 by multiplying my 2/3, don't I? Isn't it 2/3 of a 1 give me 2/3? Because half of a 2 gives me 1, and 2/3 of a 1 gives me 2/3. So there we go. But we have 2/3, this is now 1, right? No, 2. I've got 2/3 of a Cl3 of 3 chlorines. 2/3 of 3 is 2, which balances the 2. And I've got 2/3 of a nitrogen, and that is 1 of a nitrogen, so I need 2/3 of that, so I multiply that by 2/3. Okay? Is it balanced? Yes, it is. Let's look at, I've got 2/3, and I've got 2/3 of a half, which reduces down to be 1/3, right? I've got 2/3 of my original molecule, produces 1/3 of a nitrogen molecule, and 1 chlorine molecule. How do I get rid of that coefficient? I get rid of the coefficient because I've got common denominators by multiplying by the denominator. In this case, the denominator is 3. Let me multiply across by 3. If I multiply this by 3, I get 2. If I multiply this by 3, I get 1. If I multiply this by 3, I get 3. How do we do? It's right. It's the same thing as before. But you see how this case, using the other method is quicker and easier, and using the fractional is longer and more complicated and more prone to error. So I always start with the other one first. I tend to use the method that I teach first, and if it gets too complicated, like the one question on the final that we had, then I will stop and go back to using fractional. And frankly, I just oftentimes just move between the two, because I realize that mathematically I'm doing the same thing whether I multiply by a whole number or I multiply by a fraction. As long as I remember at the end to go back and make sure that my balanced equation does not have any fractional coefficients, we'll be fine. You have to do an appropriate mathematical step every step of the way. The more steps, the more possibility of error. But as long as you've got a good process, it'll work out, it'll be fine. Let's go ahead and I'll flip back just a bit. I've got in my notes that this relates back to review question number 1. Review question number 1 asks, can an element undergo a decomposition reaction? Can an element undergo decomposition, yes or no? And explain your answer.
No.
Okay, Will says that an element cannot go through a decomposition reaction. Is he right? Is Will correct? Will says that an element cannot undergo decomposition. So what is the definition of decomposition?
A reaction that changes a compound into its constituent element.
A reaction that changes a compound into its constituent elements in the elemental form. So can an element undergo decomposition? No, it can't. As a matter of fact, that's what we said before, Dalton, using that theory, said the reason how we understood that an element existed is because we could not decompose it any further. We took something that was a compound, a molecule of more than one element, and we broke it down into elemental forms. Then we came to understand the idea of an element because we couldn't take it and break it down any farther. And so no. Review question number 1. Can an element undergo decomposition reaction? No, it cannot. Why? A decomposition takes compounds and reduces them down to elemental forms. An element is already in its elemental form. It's got no place else to go. Looking over to the right hand on practice problem number 1, it asks you to write a balanced equation for the decomposition of RbNO4. So we're on practice problem number 1. It says, RbNO3. What is that? RbNO3. Well, rubidium over here is column 1 element. And I know that NO3 is some form of what? What do we call that? PAI? A polyatomic ion, right? NO3, huh? Now, if this is a correct notation, we know that that polyatomic ion has a what charge?
I don't know.
How negative?
Negative what?
1. That's negative.
Negative 1, right? Because rubidium is a column 1 metal, and it becomes a positive 1. So it needs a negative 1 to balance it out. So we have an ionic bond between the rubidium and this polyatomic ion, and that polyatomic ion is not ionically formed, it's covalently formed because it's all non-metals. Okay? I'm just trying to go back so that some people think, glad we're done with module 4, don't have to remember that anymore. Guess what? Here we go. All right, so we're going to break this down. The question is, write a balanced equation for the decomposition of this molecule. All I do is look from left to right and decode all of the elements. So after I break down the molecule into its constituent elements, I ask myself, what question first? Are any of them homonuclear diatomics? And if they are, represent them as such. Rubidium, homonuclear diatomic? No, like I said, it's a column 1 element. It's a metal. Nitrogen?
Yes.
Yes, it is. Oxygen?
Yes.
Okay. So, break it down. First step. Second step, ask the question. Homonuclear diatomics, yes or no? If yes, indicate so in the product side. Third, is it balanced?
So,
No, I can see quickly there's only 1 nitrogen and there's 2 over here, there's 3 oxygens and there's only 2 over here. Rubidium's fine. But because it's not balanced, now I need to set up my matrix. Rubidium, nitrogen, and oxygen. I know that if I account for everything over here, it should include everything over here because remember, we cannot create or eliminate any element. We can't break it down any farther and form some new element. What we're doing is just rearranging the building blocks. We're taking one structure and breaking it down. Think of it this way. We're taking a Lego structure and we're breaking all the pieces apart as far as we can, and then we're grouping them by color. Okay, so this would be like 1 red, 1 blue, and 3 green. If we break that up, what does it look like in the different piles? Knowing that when we have certain blocks, certain colors together, they're always going to bond up in sets of two. That's just one of the things that doesn't quite fit that metaphor. All right, so rubidium, nitrogen, and oxygen. On the reactant side, for the rubidium, we have how many? One nitrogen, oxygen. Does everybody see that?
No.
Okay, this is review, I know. Only thing that's new here is this. Everything else is repeat. Reactants, products. Okay. On the product side, rubidium, nitrogen, oxygen.
2.
See how good I am ignoring you. So 113 and 122. Were you saying 8? That's what it sounded like to me. I don't know. Oh, okay. So it was absolute nonsense, not just partial nonsense.
Exactly.
Okay, good. You've got that down. Okay. Somebody from over here, where are we going to go? What do you want to do? What do you want to approach first? Do you want to use the whole number method by counting up, or do you want to use fractional to bring them down? I'm looking just to the corner right here. Somebody in here make the decision. Where are we going? Whole numbers. Okay, so what we're going to do, using the whole number approach, is we're going to look to where we have too few and try to bring the count up, right? Okay, so where do we have less that we need more of?
Nitrogen.
Nitrogen, all right. So looking at nitrogen, we have too few on the reactant side. We need more to balance the product. We have 1, we need 2, and how do we do that? Keep going, you're doing good. I have 1 and I need 2. So how do I get 2? Good, add a coefficient of 2. Right. By putting that coefficient in front of the molecule, however, I've increased the element count for every element in that molecule, right? So we need to go ahead and count for that. Rubidium now we have 2, nitrogen 2, and oxygen we now have 6. So using the method, somebody else from that corner, we've decided we're counting up with whole numbers. We need to find out where we're lacking and get more. Where are we lacking? Where are we lacking and where do we need more? Rubidium, we have 2, we need 2, right? We only have 1. And we accomplish that by putting the 2 in front of the molecule. Are we balanced yet? Okay, one more person from that set back here. Yes, sir.
You can put a 3 in front of the O.
3 in front of the oxygen. That will affect only the oxygen. And in that case, I have 3 sets of 2, which is 6. Okay. Are we balanced now? Yes, we're balanced. 2, 2, 6. Equations are balanced. I always have to go back now, one more step, which we often forget. Okay. Now that it's balanced, I go back and see, do I have any fractional coefficients? No. Okay. Next question. Is there a greatest common factor for every one of them? What is that? The greatest common factor for every one of them is 1, right? If I see a 2 and a 3 and a 1, 2s and 3s there's not common factors between them other than 1. And if the only common factor between all the coefficients is 1, I'm done. If they were divisible by 2, all divisible by 3, whatever the case may be. The easy cleanup is to go through and see that they're all even, divide by 2. Okay, and then go from there. So, write the decomposition with the molecule and then the elemental forms. I can break down all the symbols and then ask myself the question, are there any homonuclear diatomics? If there are, show them as such by writing them in their homonuclear diatomic form, their elemental form. Then I go back through and I either find where I'm lacking and multiply them by adding coefficients, whole number coefficients, or find where I have excess and multiply by fractional coefficients. When I'm done with that and I have a balanced reaction equation, I look at the equation and ask myself, are there any fractional coefficients If there are, eliminate the fractional coefficients. Then look back through the coefficients and ask myself, what is the greatest common factor between the coefficients? If it's 1, I'm done. Okay? Any questions on decomposition reactions? Tomorrow we're going to start on formation reactions, which is the opposite, which is where rather than having the molecule and breaking it down into its parts, I take the parts and I build the whole. Same thing in reverse. Okay?